Okay. Last revision class of the semester, and probably also my last revision class for you. Next semester, somebody else will take the revision classes, most probably. I've got to get in some young blood. So, you'll see. Okay, today's tutorial is on pulleys and relative motion. But as I said to my class, don't just sit with all the pulley problems. Do one or two of the pulley problems and then go over to the relative motion. And then you can always come back to the pulley problem. I suggested something like this to my class. Do number 1, 2, and 8, I think, are pulley problems. And then some relative motion, and then you can come back to some pulley problems. And yeah, so don't sit the whole afternoon just doing pulley problems. Okay, first one here is one of the examples in the book, so you can just follow it here. And what I want to say more about it is the basic principles. First of all, you need a coordinate system when you're working with pulley problems. So you've got to decide where your datum line is. The datum line can be at the roof, right at the top, or it could be over here, or it could be down on the floor. And from that datum line, you measure your distances. Datum line, in Afrikaans die gewoonlik die verwysingslyn, of hulle praat ook van die datumlyn. You can ook praat van die datumlyn. So first of all, your datum line. Then in this case, you have 2 ropes. So if you have 2 ropes, you need 2 equations. If you have 3 ropes, you need 3 equations. 1 rope, you need 1 equation. In this case, you have this rope here on the outside, and then that one there on the inside. This point A here could be any point on this rope. In this case, it looks like it's at the same height as that point over there, but if you pull this down, then this distance SA is going to get larger and the SB is going to get smaller. So you can't say this is SA and that is SA, or that is SB and this is SB. In this, at the moment, they're the same, but A could be any point on that rope. And then the last thing, yeah, that I measured, that I mentioned, you can take the datum line from the bottom. Important about this datum line is if you measure it down from the datum line, like SA, that is the positive direction. So if the velocity is in that direction downwards, like here, then it's a positive velocity. If the velocity was upwards, then it would be a negative velocity. The same for SB. Now this SB is this pulley plus this weight, this whole thing here. That we see as B. Yeah, we don't bother about the sizes of the pulleys or whatever. So this whole thing moves as a unit. So you can take the B distance to there, or you can take the B distance right down here. Okay, in this case, then for the 2 ropes, the first rope, the inside rope, would be that distance there, plus that distance there. And that is the SB plus the SC. SB is actually that distance plus that distance there, but that's a constant. If you have constant distances, the same as this distance around here, and that distance around there, they are all constant distances. So you don't have to add the constant distances here. You can, but then you take all the constants to the right-hand side, and you have 1 constant on the right-hand side. And the other rope is this distance here, and that distance there, and that distance there. So this distance here on the outside is SB. This one will be SB minus SC. This one in the middle. And that one will be SA minus SC. So then you have all those distances. SB on the outside, this one SB minus SC, and then this SA minus SC. And they are all a constant. Because your rope is a non-elastic rope. The length of the rope stays the same. It's not going to change. The relative distances are going to change, but the total length of the rope is not going to change. And as I say, you can add this constant distance here and this one over here, but it's just a constant on the left-hand side. You take it over to the right-hand side, it's still a constant. So that one, if you simplify it, you get this equation. And, okay, if you differentiate those two equations, you'll get from the first one, you'll get that one there, VB plus VC. You differentiate with respect to time. So that one there, because SB is a function of time and SC is a function of time. They're going to change all the time. And then the other equation, this one here, 2VB minus 2VZ plus VA is 0. So now you have these two equations, and they want the relation between the velocity at A and the velocity at B. So they're looking at the velocity of A and B, those two. So you've got to get rid of C. Now it's quite easy in this case to get rid of the velocity of C. Velocity of C is minus the velocity of B. So you get it from there, you substitute it back into this equation, and then you get the relationship between the two velocities. Okay, so two ropes, two equations, differentiate them and simplify, get rid of the velocity you don't need in this case, or which they don't ask, and you get the relation between those two. So in this case they say VA is 2 meters per second and is a positive velocity because it's down and you're measuring down as positive. So it's a positive velocity there. So VB will of course be a negative velocity. If that one's going down, that one should go up. So it's minus or half, or you can write it like that. Okay, so that's the basic theory for any pulley motion. And you're going to get some of those. Okay, another one, a little bit different, is like in problem 8. In problem 8, you have this one. Mass B and a mass A. And if you check this rope, you'll see it's one rope. One rope going all the way around. It's one rope. So with one rope, you need one equation. Okay, what do they give you in this case? They give you the X and the Y. And from the drawing, it looks like X and Y are the same height, but once again, when this one moves down, that one's going to move up. So you can't take this as X and that as X. It's got to be different from each other. This pulley could just as well have been somewhere down here. So one equation you need, and it's quite easy. There's an X and an X, and an L1, and an L1, and an L1. I just call them L1. So you're going to get something like that. Your total length is going to be 2x here on the left-hand side and 1, 2, 3 L1s. And okay, you want a relation between x and y. Now this L1, you can use Pythagoras. That distance is L1 and that distance is B. So this is going to be the square root of y squared plus b squared. I didn't do it any further, just the first important step. So now you can get L1 in terms of y and b. B is a constant, so you're going to get an x and a y here. You can take all your constants to the one side, and you're going to have an x and a y, and then you can differentiate from there to get the velocity in the x direction and the velocity in the y direction. Okay, then another problem where you have this thing at an angle is this one, which is a bit tricky. But let me just say 2 or 3 things about it. Once again, you have one rope. So one rope means one equation. Here I've given you the YB. So your datum line is there at the top. You're measuring from there, there's a YB, and you have another datum line here in this direction, XA. This person is moving to the left at an acceleration, a constant acceleration of 0.2. So there's your rope, and you can write down the equation for that rope. It's going to be this distance plus that distance. So you're going to have something like that. The length AC plus the length YB. Now, LAC you can write in terms of X and 8. That distance is 8. So once again, Pythagoras. A bit similar to the previous problem. This LAC, this side, the hypotenuse, whatever, skuinsy. Nice word in Afrikaans, skuinsy. LAC, that's going to be square root of that. You have this distance is 8, so 8 squared plus YB. And they give you the total length of the rope as well, 16. Okay, now you can differentiate that. I didn't do it here, I only differentiated the left-hand side. That's 0. That part you can do for yourself. And then you'll get a relation between the velocity of A and the velocity of B if you differentiate that. You're going to get the velocity of A and the velocity of B. So that's the first basic steps here. Now the question here is, they say this boy is moving to the left at a constant acceleration. He starts from 0, he starts from rest. So okay, here in this direction you have a constant acceleration case. Something starting from rest, constant acceleration, moving a certain distance. And they want to know eventually, what do they want to know? They want to know, determine the speed of the boy at the instant when YB is 4. When this is 4. So this one is moving up. When that distance is 4. Now when that distance is 4, I can get XA. That's important. You need that. Of course, I give you this. When YB is 4, you can get XA. So he's starting from rest, he's moving at the acceleration, and you can get the XA, how far he's going to move. So you can use the equation like, well in this case you'll probably use the equation V squared is V0 squared plus 2AS. He starts from rest. He's moving at a constant acceleration. You can work out this distance because they say YB is 4. When YB is 4, you can get the distance, and then you can get his velocity. And once you have his velocity, then you can get the boy's velocity. So that's now given away the whole reasoning here in this problem. So okay, let's get away from that. You can see if you can do it. Okay, a few things on relative motion. Okay, let's say you have two things moving, one at 4 meters per second and the other at 10 meters per second. 20 degrees, 60 degrees. And the question is, what is the velocity of A relative to B? Now, when you do a problem in relative motion, it's important to always write down some equation, some relative motion equation. Don't just think what I'm going to do. Start with writing down the equation. Now there are two methods you can follow. One is what we call the scalar method. That is when you make a drawing of these velocities. And you say, okay, now there are two ways of approaching this. They want the velocity of A relative to B. Now, you can get it from this equation. Velocity of A, when you have an A on the left-hand side, you have A, B, A, B. So it's easy to remember. So when you want that, you need the velocity of A minus the velocity of B. Now, how do you get the velocity of A minus the velocity of B? This is actually, let me write it like this. You can also say this is the velocity of A plus the negative of the velocity of. Now the negative of that velocity is that same 10 meters per second, but in the opposite direction. So you can make a drawing of this. You can take that vector and you can add this vector to it. And the resultant of those two vectors should give you this. Same as you did with forces. When you have one force, you add another force to it, you get a resultant. You can do it either by using the triangle rule or the parallelogram rule. So here we're going to use the triangle rule. So the velocity of A is in that direction, and the minus the velocity of B is going to be in the opposite direction of that drawing. So you're going to have the velocity of A, and you add to that minus 10, or the vector 10 in this direction. And the resultant of those two should be velocity of A relative to B. And that's what you're looking for. So the velocity of A plus that one. So this is what they call the scalar method. Now you just have to solve it, the cosine rule and the sine rule, and you just work out what is the magnitude of this velocity. Or, what you also can do, in this case, still talking about the scalar method, you can also say, use that equation from the start. If I have the velocity of B, which I have, and I add to that this one I don't know at the moment. I know that one and I know that one. So the velocity of B is something like that. Now this equation tells me if I add something to that, I'm going to get the velocity of A. Now the velocity of A is there. And the velocity of A should be the resultant. So the velocity of A is somewhere over here. So that one plus something, so that something has got to be over here. That line will be the same as this line. And you have the same slope and the same magnitude. So this line plus something, now I don't know the something, but I know the resultant is going to be here. This one on the left-hand side, the resultant. So that is the velocity of A relative V. And it's going to have the exact same direction and magnitude as this one we had over here. So there's these two ways you can use when you're using the scalar method. Just let's go back a moment. You say, okay, I want this one, VAB, so it's the difference between the vectors, or it's a vector plus minus that vector. So a vector plus the negative of the VB, those two, the resultant of those two is VAB, so you get that. Or you can go use your original equation and say, okay, I've got to add something to this. I don't know what it is, but I know the resultant. Remember, your resultant always starts at the same point where that vector starts. Or that vector, yeah, well, you can draw it another way, of course. But let's take it where that vector starts, plus something, there your resultant is. So that's a scalar method, or you can use the vector method. Now the vector method means you write each one in terms of their I and j components. So you're going to say, like VA over here. It's got an I component, it's got a j component. So you write it like that. V cos 20 and V sin 20. And the same for VB. VB is minus 10 cos 60 and plus 10 sin 60. And then, okay, the one you're looking for, VAB, is going to be the difference between the two. So you can work that out. Now, there are some people prefer doing it this way, especially when they have difficulty drawing these diagrams. These diagrams are the easy way. I usually prefer to do this, to make a vector diagram. Yeah. But okay, you can have a look today. Especially when you're working with a velocity, then the diagram is easy. When you're working with an acceleration, the diagram gets a bit tricky. Okay, and then you just solve it from there, and you get these two components, and you can get the magnitude and the direction, all those, if you use that method. Yeah, before I get to acceleration, here's just another odd problem. Something people often have a problem with. Let's say, well, I've got VM here for a man, it could just as well as being a girl, is moving along here and hitting a ball in that direction. What is what in this equation? Okay, this one we have. There. What is this? Is this the velocity of the ball, or is this the velocity of the ball relative to the man? Now remember that ball has a horizontal component when it's hit in that direction. It has this horizontal component. So what you actually have here is, that is not the velocity it is hit at, that is going to be the velocity of the ball, or let me rather say it this way. This ball is not going to move in that direction, because it's got a horizontal component. If it had no horizontal component, and you just hit the ball from a stationary position, then it would move in that direction. But now it's got a horizontal component. So what you're going to have here, you're going to have something like this. Velocity of the man, and the velocity, that one is going to be the velocity of the ball relative to the man. No, sorry, this is going to be the velocity that's going to be the final velocity of the ball, that one, and this is going to be the velocity of the ball relative to the man. So if the man was stationary, then the velocity of the ball would have been that one there. But because of this component, you're going to get that. So this one, that's the velocity of the ball, that's the velocity, that's the velocity of the ball, that's your final one. You can draw it different ways. You can say, velocity, let me just check here, am I doing the right thing? That's the velocity of the man, plus the velocity of the ball relative to the man is actually that one there. So the velocity of the ball. Oh, I'm sorry, I'm wrong here. Wat maak ek nou foutjies hier? Ja, dis my dieselfde van die bal. Ja, hierdie relative. Yeah. He's hitting the ball. Yeah, sorry. The man is moving in this direction. Let's say he hits the ball at 60 degrees. Relative to him, he hits the ball at 60 degrees. That's going to be the final velocity of the ball. I think we have a problem here. So that's exactly that equation. I don't think there are any batteries here. Let's have to speak up. Okay, so you have that equation there. The man plus that vector is going to give you The accelerations are often the difficult part of these problems. Well, not really difficult, but a little bit different. Different in this sense that, especially when something moves around a curve, then you have an extra acceleration. You have the normal acceleration. So, for example, in this case, you have an acceleration in this direction, the acceleration of A. They give you the acceleration of A. This is problem 14. Problem 14. Two cars, they give their speeds, that's 30 and 40. B is increasing at 2 meters per second squared. So this acceleration here is 2. It's increasing its speed at 2 meters per second squared, and while A maintains a constant velocity, so you have no acceleration here. But here you also have this normal acceleration. That one there is the tangential acceleration. This one here is the normal acceleration. So that one is actually the tangential component. The normal component, and the normal component, as you know, is the velocity squared divided by the radius of curvature. So, they ask, what is the acceleration of B relative to A? So you need the acceleration of B, but the acceleration of B has those two components. The acceleration of A is 0 in this case. But the acceleration of B has these two components. It's always a good idea to make a little drawing and to say, okay, I know that one is 2. And this one is, this normal component is the B squared over rho. B squared is 30 squared. That's right, 30 squared. And the radius of curvature is 200. So then you can work out what this normal component is. And here it's the best to work with I and J components. To write this resulting acceleration here, you have these angles. That will be 60 degrees. And these are perpendicular, so that will be 30 degrees. The normal and tangential components are perpendicular. So now you can write down what is the x component of that one and the x component of this. You add them together, and the 2j components, and you that one minus that one, and then you get the resulting acceleration there. And once you have that, you can work out the acceleration of B relative to A. Okay, let me just get to another important problem. You have a similar one in the, well, this is probably the one in the tutorial. Yeah. Oh, before I get to that, just problem number 12. Problem number 12. These cars, that one is moving in that direction, and this one is moving in that direction. Just if you're not sure. So that one is going south, and that one is going north in the right-hand lane. So, okay. Okay, problem 11. Problem 11. I think you did something similar in class. You have a river flowing at 2 meters per second. And this guy wants to steer his boat from A to B, or he wants to start at A and finish at B. Now, in which direction should he steer the boat so that he gets to B? So, okay, your equation here is going to be the velocity of the boat is the velocity of the river plus the velocity of the boat relative to the river. That's your equation. And once you have that equation, then you can figure out how to draw this diagram. Well, the velocity of the river is obvious at 2 meters per second. Let me just, sorry, I'm off the page. Let me go to this side. The velocity of the river is going to be that one. Now, what is the velocity of the boat? Is the velocity of the boat the velocity along this line, or is the velocity of the boat the one at that angle theta? The velocity of the boat is the final velocity of the boat, the final velocity and direction. So you're going to steer the boat in, say, this direction. But now the river is going to take it down in that direction. So the resultant is going to be here. Now they say the boat can steer at 5 meters per second in still water. Now that, what they mean by that, that is the velocity of the boat relative to the river. That is this one here. And in my drawing here, that is going to be this one here. Boat relative to the river, and this is the velocity of the river. So that one is 5, and this one is 2. Your resultant is that one over there. It's very much the same as the previous one I had here of the guy hitting the ball in a certain direction. Now, yeah, you want to move in that direction, that's got to be the final velocity of the boat. So first that one plus that one. And in this case, it's much better to solve it by using this triangle here, this inside triangle here. Solve it by using the triangle. If you solve it by using the I and j components, you get an equation with a sine and a cosine in it. And here's a better drawing than the one I have there. This one here. That one is the boat in still water, 5 meters per second. The river takes it down here, and that is the final velocity of the boat. And now you just use all those distances. They give you a 50 meters here and a 50 meters there, and they give you some angle, I think. Yeah, no, only give you that 50 meters and 50 meters. So solve this problem by using this diagram, or a similar diagram. As I say, if you solve it the other way by using what we call the vector method, you get a sine and a cosine in the same equation, and then it's a bit awkward to solve it. Yeah, then you've got to use something like Newton's method to get that angle theta. Yeah, I think that is more or less everything. Yeah.